Okay, so for the first one, let's say we have an object that's connected to the wall by a fixed joint. Let's say this angle is 50 degrees. And a cable is connected to the end of this beam that goes over a pulley. And the other end is connected to a mass of 200 kilograms. The length of this beam is 2 meters. And something we're going to do a lot of times, and we're going to do here, is we're going to assume that that beam is thin enough that we don't have to worry about the thickness of it or the width of it in this calculation. So we'll just assume that that it sort of makes a line, and that cable is connected to the end of the line. And let's say that the mass of the beam is 100 kilograms. And we want to know the reaction loads at the wall. Yeah. Okay, so first thing we have to do is draw a free body diagram. And I guess let's first do a free body diagram of the mass and figure out, we'll see that we can calculate the cable tension with that. We have 200 times 9.81, so 1962. And then we have the cable force up. And Newton's second law says 0, negative 19.6, 1962 plus 0t is equal to, well, for us it's going to be 0 because it's statics. Okay, so the x equation doesn't say anything, but the y equation says t is equal to 1962. So now we'll do the free body diagram of the beam. This is the new stuff. At the center of the beam, we have a weight force down that's equal to the mass of the beam times 9.81. So that is 981. And then we have the cable force, and we just calculated that the magnitude is 1962. And now this is the first time in one of these problems that we're using what we know about two-dimensional joints. So with that fixed joint at the right end, is there any axis where this can translate? No, so the x and y components both have forces applied, okay? There's no axis where it can translate. Can it rotate? No, so a fixed joint eliminates all, it eliminates all 3 degrees of freedom, and that means it's gonna have 2 components of a force and a couple. So I'll write that as, I'll call that force R, reaction force, and then I'll call this couple MR reaction moment. And now, so I didn't do this when we isolated the mass because that I just did as a particle. We weren't dealing with rotations of that mass. But this is a rigid body. We do care about rotations. We're dealing with moments and stuff. So I'm going to write out the table. Row vector, force vector, and moment vector. And now we have to choose what we're going to calculate the moment about. And you can choose any point you want. I'm going to choose this point here, but any point would work. That's the other place where statics makes you a little sloppy, because in dynamics, you only have a couple of choices about where your about point can be. In statics, it can be anywhere. Okay, so the red is the about point, and let's just go through all these loads and fill out a row for each one. So first I'll deal with that reaction force R. The row vector is the vector from the about point to where the force is applied. So what's that in this case? Yep. So 0, 0, 0. For the first couple of these, I'm going to write it all down as components, and you'll see patterns with those as we go. And the R vector is Rx, Ry, 0. And cross product then is 0. Next, I'll do the couple MR. For a couple, you don't care about these. That only has a Z component, so this is 0, 0, MR. And now I'll go to the weight force. So we have to figure out a vector that goes from the about point to where the weight force is applied. That's the center of the beam. So to do that, I'll draw the coordinate system. And first on that coordinate system, I'll draw the vector where that angle is given. Okay, so we know that it's 50 degrees from a downward vector like that to a vector over like this. So that's what I'm going to draw. Okay, so from the negative y-axis to this is 50 degrees. Yeah, so now the angle that we want is from the positive x-axis to this. So that's 270 minus 50. So that angle is 220. The length of the cable, the length of the beam is 2 meters. So the distance to the middle of the beam is 1 meter. So for the weight force here, we have 1 times cosine of 220, 1 times sine of 220. That is negative 0.766. And negative 0.643. The weight force is 0, negative 981, 0. And the cross product between those two is 0, 0, and then a Z component of 751.4. Let's see, and then we have the 1962. So that's going to be 2 times cosine and sine of 220, or twice this. So that is negative 1.53263. 1.5. And negative 1.286. And then 0. The weight force is 0. Positive 1962, 0. And the cross product is 0, 0, and then a Z component of negative 3790.6. Okay, so now that we have all these forces and moments, that's all the loads in the free body diagram. Now we're going to use Newton's second law that says add up all the forces, and that has to add up to 0. And we're going to use the rotational Newton's second law, the moment equation, that says add up all the moments about A, that also has to be equal to 0. Okay, so that's what we're going to do now. So first, Newton's second law. We're going to take all of the forces here, and that's going to be the left side of Newton's second law. So we have Rx, Ry, 0, plus 0, negative 981, 0, plus 0, 1962, 0, and that's all the forces, are equal to 0, 0, 0. Yep. No, pretty soon I'm gonna stop including that too. But I want to do at least one where you see how it just ends up being, like in a way, everything is a 3-dimensional problem. It's just certain components just end up being useless, you know. Okay, so from this, you get that Rx is equal to 0, Ry is equal to negative 981. Rz is 0. And so that reaction force is 0, negative 981. I'll leave the Z on there for now. Newtons. Okay. And now the moment equation, the torque equation. By the way, you said the torque equation. Physics people tend to use torque and moment interchangeably. In structural engineering, in mechanics, people don't tend to use torque that way because the torque is a specific, it's a equal and opposite moment on 2 ends of a rod, you know, something that would cause a twisting stress on it. So anyways, I'm going to always use moments, but yeah, in engineering, it has a specific thing. Physics people, it doesn't, because they don't care about specific things. Okay, so now we're going to use the moment equation. And so we're going to add these up. So we have 0, 0, 0 plus 0, 0, MR, that's the couple, plus 0, 0, 751.4 plus 0, 0, negative 3790.6 and we got these from that column of the table. And these add up to a 0 vector. The first two equations don't help. But the third equation says MR is equal to 3790.6 minus 751.4. So I think that's 3039.2. It's all in SI units, so that's Newton meters. Okay, let's just keep rolling. Okay, so this time, let's say that there is a wall and a beam is connected to the wall by a pin joint. And this beam is horizontal. And then there's a pin at the center of the beam that slides in a slot. And that slot is in something that's fixed to the ground. Okay, so all of this shaded stuff is fixed to the ground. Okay, you follow that? And then there's a 1,000 Newton force applied to the end of the beam. And this angle is 45 degrees, and that's also the angle of the slot. What really matters is the slot. And the question is, what are the reactions at the two pins? In the middle? Yeah, right. So if there were no other connections to the ground with this beam, this thing could slide on, could go up and down, and it could also spin around. And let's see, the mass of the beam also, there's, let's say this beam has a mass of 50 kilograms. All right, so first we'll draw a free body diagram of the beam. Oh, I didn't give a length, did I? We need a length. 1 meter. Okay, so what kind of loads are applied? Well, there's a weight acting at the center. That's 50 times 9.81, so 490.5 newtons. And there's a 1,000 downward at the end. And now there are two joints in this one. We have to think about the loads that each of those two joints applies to that body. So first, let's think about the pin on the left side. So a pin joint like that, is there any axis where translation is allowed by that pin? If you think of that pin as connected to the ground? No, that beam could rotate, but you couldn't move that point this way or any direction. Okay, so that means there's a full vector of forces applied by the pin. So I'll call that, so there's a full unknown vector, I'll call that RL for left. Sketch this slot in. This is at 45 degrees. And the force is perpendicular to that. And I'll call that RR. That's a scalar because we know the direction. And now we have to think about rotation. If everything else was removed from this problem, would this beam be able to rotate around that pin? Yeah, I mean, that pin can spin inside that slot. So there's no couple applied. Okay, so now how many variables do we have? This is a complete free body diagram. This can tell us whether there's a chance that we're going to be able to solve this by statics or whether there isn't. All right, so do we have a chance of solving this problem? Well, yeah, because how many equations do we have from Newton's laws in 2D? We have 2 for Newton's second law, 1 for the moment equation, so 3 total equations. That means we can solve for 3 variables, and that's what we have, 2 components of RL and 1 of RR. Okay? And so now I'm going to write out this table, row, force, moment. All right, so we have to choose an about point. I'm going to choose this, but you could choose anything.
Why would you choose that one? Do you have like a strategy?
Kind of. It really doesn't matter that much, but sometimes if you put the about point at the place where you have the most unknown force components, it'll uncouple the system of equations, and you can solve it equation by equation instead of solving it as a system. Okay, so the first load I'm going to deal with is RL. The row vector is 0, and I'll leave off the Z component. And the force is RL, RR. And now you can think of the cross product as just this times this minus this times this. Whoops, I did that wrong, sorry. This should be RL. RLX and RLY. That's what happens when I'm like talking while I'm trying to think of what I'm going to say next. Okay, but the cross product, 0 times this minus 0 times this, so 0 moment. And remember, that's a z component, really, but I'm giving it like it's a scalar. And then we have the weight force. The vector from the about point to where the weight is applied is positive 0.50. And the weight force is 0, negative 490.5. And the cross product is negative 245.25. And then we have RR. That's happening at the same spot as the weight, so that row vector is also 0.50. Yeah, we do, exactly. Okay, so to figure out that vector, I'm going to draw out the coordinate system. And first, I'm going to draw the vector where the angle is given. So that 45-degree angle is given between the horizontal and a vector like this. Okay, so like this one would have a theta of 45 degrees. Does everyone see how that relates to what's given in the picture? And now the vector we want is another 90 degrees counterclockwise from the one I drew here. So now I'm going to draw this one, the one we want. And we know this is 90 degrees. And so theta for this is 45 plus 90, so 135. And so yeah, 135. So we have, so this vector is going to have a magnitude of RR. So it's going to be RR times cosine and sine of 135. And that's negative 0.7071 RR, positive 0.7071 RR. So then that's the force. And now the cross product is positive 0.3535 RR. And then the last one is the 1,000 Newton force. The row vector for that is positive 1, 0. The force is 0, negative 1,000. The cross product is 1 times negative 1,000 minus 0 times 0. So that's negative 1,000. And now Newton's second law, just add up all the force column things and set those equal to 0. Rotational equation, add up all the moment column things and set those equal to 0. So Newton's second law says RLX RLY plus 0, negative 490.5. Plus negative 0.7071 RR, positive 0.7071 RR, plus 0, negative 1,000, 0 is equal to zeros. And you can't solve for anything yet. And now the moment equation says negative 245.25 plus 0.3535 RR minus 1,000 is equal to 0. So you can use the moment equation right away to solve for RR. And you get 3522.6 newtons. And then plug that value for RR into Newton's second law. And for RL, you get 2490.9 in the x direction and negative 1000.5 in the y direction. Any questions about that? Okay.